Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from Latent Space. Yi-Tae from Google DeepMind shares technical arguments that challenge core assumptions in AI engineering. His team's Math Olympiad Gold Medal achievement rests on principles that contradict industry consensus, rejecting specialized architectures in favor of monolithic models, replacing human imitation data with self-generated training loops, and decoupling domain expertise from system performance. We examine the technical logic underlying each claim. Yi-Tae from Google DeepMind recently articulated a set of engineering principles that force reconsideration of how AI systems achieve expert-level performance. His analysis begins with architectural decisions surrounding the International Math Olympiad achievement. Standard engineering consensus holds that rigorous mathematical proof requires specialized neurosymbolic systems. The prevailing architecture pairs language models with separate formal verification engines, operating under the assumption that statistical pattern matching cannot handle symbolic reasoning. Yi-Tae's team demonstrated this assumption was incorrect. They achieved gold medal performance using a single general-purpose Gemini model without specialized mathematical components. His technical reasoning centers on parameter encoding. External tools like calculators or formal verifiers represent computational functions that can be absorbed directly into model weights. A sufficiently scaled model does not require external calls to mathematical verification systems because those verification procedures become encoded within the model's internal representations. They integrated the lean formal verifier into the chain of thought process itself. This represents a fundamental shift in system architecture. Rather than building modular pipelines with distinct specialized components, the approach consolidates all computational functions into a single neural network that internalizes every previously external tool. This architectural philosophy connects directly to his second technical claim regarding training methodology, specifically the transition from off-policy to on-policy reinforcement learning. Current training paradigms rely heavily on supervised fine-tuning, where models learn by imitating human-generated solutions across millions of examples. Yi-Tae characterizes this imitation phase as a temporary bootstrapping mechanism that must eventually be abandoned. His position holds that genuine capability emerges through on-policy reinforcement learning, where the model trains exclusively on its own generated outputs rather than human demonstrations. The mechanism operates as follows. The model generates a solution, verifies correctness through formal methods, and updates parameters based on its own trajectory rather than human examples. He draws a concrete analogy. Watching instructional videos teaches you about tennis, but actual skill development requires physical practice with direct feedback. On-policy learning implements this direct feedback loop where the model iteratively improves through self-generated experience rather than passive observation of human behavior. The striking implication here is that human data functions as initial scaffolding that eventually constrains model capability. To achieve superhuman performance, the system must stop learning from human examples and begin optimizing against its own performance metrics. This suggests human demonstrations represent a ceiling rather than a foundation for advanced capability. This training philosophy extends into his third claim, which addresses the role of domain expertise in AI research. Traditional system development assumes that building expert-level AI requires domain specialists who understand the target field. For mathematical problem solving, this would mean hiring mathematicians who comprehend number theory and combinatorics to guide system design. Yi-Tae states explicitly that he possesses no knowledge of the Math Olympiad, cannot solve the problems his system addresses, and does not understand the mathematical content of his model's outputs. Despite this complete absence of domain knowledge, he served as a captain for the team that achieved gold medal results. His claim is that AI research is fully separated from subject matter expertise. You can construct systems that outperform world-class domain experts without understanding the domain itself. The relevant knowledge is not the subject matter, but the dynamics of neural network training. This creates a categorical shift in what constitutes expertise. Understanding the task domain becomes irrelevant compared to understanding optimization dynamics and model behavior. The model serves as a universal function approximator that eliminates the need for human semantic understanding of the problem space. This decoupling of understanding from performance leads to his fourth observation about software engineering practice, which he terms vibe coding. Traditional programming enforces a strict verification principle. You must understand any code you deploy to production. Yite describes a workflow where he encounters bugs in machine learning jobs, submits error messages to an internal AI tool called anti-gravity, and deploys the suggested fixes without reviewing the code or verifying the logic. He simply trusts the output and relaunches the job. This practice violates fundamental software engineering principles that have governed the field for decades. Computer science is built on deterministic verification and human comprehension of deployed systems. Yite argues we have crossed a utility threshold where blind trust in AI-generated code is more efficient than human verification. He treats the AI as a senior engineer whose work does not require review. This suggests software engineering is transitioning from a discipline centered on logic and syntax comprehension to one focused on delegation and management, where humans no longer need to understand underlying mechanisms to operate systems effectively. However, Yite introduces a critical counterpoint to this optimism through what he calls an existence proof that current methods remain fundamentally inefficient. The industry currently faces concerns about data scarcity, operating under the assumption that training advanced models requires trillions of tokens scraped from the internet. Yite contrasts this with his 2-year-old daughter. A human child achieves reasoning and generalization capabilities that exceed current large language models while learning from a dataset orders of magnitude smaller than what AI systems consume. This represents an existence proof that the laws of physics permit highly efficient intelligence creation. The implication is that despite trillion-dollar data centers and massive energy consumption, current methods are fundamentally wasteful. We are brute forcing intelligence through off-policy imitation, while biological systems have discovered learning algorithms that are exponentially more efficient. The transformer paradigm, while successful, represents an incredibly inefficient approach. He argues the future requires discovering the mathematical principles that allow biological brains to achieve more with less. This means shifting focus from acquiring more data to extracting more computation per token, squeezing additional reasoning from each piece of information in the manner biological minds operate. Finally, Yite connects these technical positions to an epistemological principle regarding belief updating. Most individuals update beliefs incrementally. Encountering evidence that contradicts a long-held view typically results in minor confidence adjustments. Yite argues this represents a fundamental error. He cites his own experience ignoring image generation models for a decade until Stable Diffusion emerged. When a single counterexample invalidates a core assumption, such as machines solving mathematical proofs without symbolic engines or children learning language without internet-scale data, he believes you should not adjust confidence by small increments. You should update by 50% or more. His reasoning is that a single black swan event invalidates the entire model of reality you are operating under. He advocates for a high learning rate in human cognition, an aggressive willingness to discard decades of accumulated intuition the moment a fundamental limit is breached. Examining these technical positions reveals a consistent principle. Yite evaluates systems based solely on measurable input-output relationships, disregarding established conventions, whether abandoning the requirement for domain experts to solve domain problems or eliminating human verification in code deployment. His framework holds that if the model can perform the task, previous human-centered rules no longer apply. The open question is whether, as these models develop autonomous learning capabilities and solve problems beyond human comprehension, we possess the institutional frameworks to delegate control effectively. If you're interested in the video featured in this episode, click the link below to watch the original.